Okay, so page 604, number 1. 608, excuse me, number 1. Has a mass of 0.525 kilograms, oscillating at the end of a spring, having a force constant, so a force constant or a spring constant, K, of 85 newtons per meter. What is the period of oscillation? So it's just T equals 2 pi root, and then you have to pause and say, is it M over K or K over M? Because that's the most common mistake I find with students, and it's M over K. So 2 pi root, M is already in kilograms, 525 kgs, it always has to be, and K, 85 newtons per meter, and the reason the M has to be in kilograms is because of the newtons, right? There's a kilogram inside there. So T is equal to, when you do the math, 494, and it's seconds. And in case you don't believe that, kilogram over a newton per meter, dividing by a fraction is the same as flipping and multiplying, so a meter over a newton, and then remember a newton is a kilogram meter per second squared. So it'll be 1 over second squared. In other words, second squared, and that was all under the square root, so you get seconds. All right, number 2 says, you tie a 275 gram ball, so you have to make that 0.275 kilograms, to the end of an elastic band and stretch the band and release it. You count 15 complete oscillations. So that's N is 15 in 12 seconds. Delta T is 12 seconds. If the elastic band obeys Hooke's law, what is the force constant? So you're looking for K, but first you can find T from this, because remember, period is equal to delta T over N. And if you don't remember which one goes on top, remember you have to end up with seconds. So time has to go on the top, otherwise you'd end up with 1 over seconds, and that's frequency. So 12 seconds over 15, that's like 4 over 5. So T is equal to 0.8 of a second. But that's not what the question asked. It wants the spring constant. So then you go T is equal to 2 pi root M over K. And you want to solve for the K. So first step, isolate the radical. So divide both sides by 2 pi. Then square both sides. So this side is T squared over 4 pi squared, and this side is M over K. So bring the K up, the T squared down, the 4 pi squared up. K is equal to, right, 4 pi squared up, 4 pi squared over M, T squared down, or times M over T squared. So K equals 4 pi squared, M was the 0.275 kilograms, and T we found to be 0.8 seconds. Try not to forget to square that pi. You'll have it written down, but it doesn't mean that it'll end up getting squared when you punch it in your calculator. If you do end up remembering to square it, you get 16.96 newtons per meter. Okay, so that's K, number 2. Number 3. Says a 0.25 kilogram mass is oscillating on the end of a spring, having a force constant, K, of 154 newtons per meter. Frictionless surface, the amplitude is 0.34, so remember that's your X. 0.34, that's how far you're pulling it out. So if we were to draw this, right, here is it when X is equal to 0, and you pull it out to some point, and it's telling us that's our A, 0.34. Remember out here, our V is equal to 0. What is the period of motion? So to get the period of motion, you have K and you have M. So you can just do T is equal to 2 pi root M over K. So T is equal to 2 pi root 0.25 kilograms over 154 newtons per meter. And you get a t equal to 0.253 seconds. Okay, that's part A. Part B says, what is the maximum speed? So we're back to here and we're looking for Vmax. So you're going to use your energy equation, 1/2 mv initial squared plus mgh initial plus 1/2 kx initial squared is equal to 1/2 mv final squared mgh final 1/2 kx final squared plus E lost. And so we already said no E lost and no mgh's. I'm going to call this my initial here, just because I'd like to. And so out here there's no speed, but there is an x. And then this one would be my final, so in here there's a speed, but no x. And so I'm left with 1/2 kx initial squared equals 1/2 mv final squared. The halves are going to cancel, and I'm looking for the v. I'm looking for vf. So divide both sides by m. So vf squared equals 1/2 k initial squared over m. K, they told us, was 154 newtons per meter. X, they told us, was 0.34 meters squared. And m was 0.25 kilograms. And remember, that's v squared. The most common mistakes here are writing down your squares, but forgetting to square root. If you remember to do that, you will get 8.44 meters per second. Okay, that's B. There's a C. C says, what is the speed of the mass when it's 0.16 from its equilibrium position? So it wants to know, what's its speed here, where x is equal to 0.16 meters. So it's going to be conservation of energy again. So C. 1/2 mv initial squared, mgh initial, 1/2 kx initial squared equals 1/2 mv final squared, mgh final, 1/2 kx final squared plus E lost. And still no E lost, no mgh's, and that really is a squared. I'm still going to keep my initial as out here, okay, because that's where I know both my x and my v. So out here there's no speed, but there is an x. And now this is my new final right here, and at this spot there's both a speed and an x. So we now have three terms. 1/2 kx initial squared is equal to 1/2 mv final squared plus 1/2 kx final squared. The halves will cancel, and I'm looking for the v final, so bring the kx final over. So 1/2 k initial squared minus k final squared, no half, I said it, but it really isn't there, divided by m is going to be our vf squared. So 154 newtons per meter. Initial was 0.34 meters squared minus 154 newtons per meter. And our final was 0.16 meters squared divided by, was it 0.25? Yeah, 0.25. And again, remember that's VF squared. You have to take the square root. And so if before the square root it's 55.44, after the square root it's 7.45 meters per second. If you want to pause and think about it, it's less than what you got in part B, and it should be because part B was the maximum speed. Anywhere else should have a speed smaller than that, and it does, so it's a good thing. All right, number 4. The maximum speed, oops, I already did that side. The maximum speed of I'm going to run out of time. A 1.45 kilogram block oscillating on the end of a spring. So here x equals 0. Maximum speed is in the middle, and it's 0.84 meters per second. If the amplitude of the oscillation is 12 centimeters, so I'm going to pull it out to a point here. x equals 0.12